So now that we understand that a species can have multiple populations, not the other way around, and those particular populations are adapted to various climates or altitude or exposure to sun and so on, or amount of rain. So a variety of ecosystems and climates and environments, then they will adapt more to that particular location. And because of that, there will be variation. And there will be variation, as you can see on the bottom here, in between members of different populations that have adapted better to one particular location on the globe. But there is a lot of variation within the population itself as well. And in particular for the variation between populations, given enough amount of time and the lack of gene flow, these populations of a particular species, it doesn't have to be humans, it could be any other organisms, could eventually speciate, so differentiate far enough that they are not the same species anymore. But later on that. For now, let's review a few very important concepts that will help you understand these microevolutionary forces. So the idea of gene pool refers to all the genes within one population. So the gene pool of the mice in United States would be very different to the gene pool of mice in, let's say, Southern Africa, and so on. So all the genes in a particular population. Now, within those genes, as we already discussed, there can be variation at the same locus, and that's what we call alleles. So allelos in Greek means different. So there are different alternate forms. You already have this in English. Alternate comes from alleles or from allelos. So alternate forms of the same genes, of the same gene at the same locus, controlling the same particular protein or ultimately trait. Depending if you are a homozygous or a heterozygous, then your genotype versus the phenotype could be identical or not. So your genetic type, or what alleles do you have into your genetic makeup versus what expression of these genes can you see at the exterior. So for example, I know for sure I'm a heterozygote for brown eyes, but all you can see is just brown eyes. So my genotype for that particular trait is heterozygous, but my phenotype is brown eyes. So we already discussed on this idea of dimorphism versus polymorphism. So if within one population at that particular locus there are only two alleles within the whole population, then we discuss about dimorphism. But if there are three or more alleles at that particular locus controlling that same heritable trait, we're talking about polymorphism. Please remember that these two words can refer to a diversity of dimorphism and polymorphism, not just to the number of alleles per locus in one population. Now, depending on which allele it's more abundant, is it the brown eye, is it the blue eye, is it the green seeds, is it the yellow seeds, etc., then we discuss about allelic frequency. And the allelic frequency is controlled by a multitude of factors that we'll talk about in a moment, such as gene flow and genetic drift and so on. But it ultimately refers to how much of one allele versus the other allele at that locus it exists in that particular population. And in this case, we're talking about dimorphism, but it could be polymorphism as well. Of course, we're comparing that one allele with the other two or multiple. So ultimately, any change in allelic frequency we refer to as microevolution. So if the previous generation had 99 to 1% of this one allele versus the other. And then the next generation has, let's say, 98 versus 2%. Then that is called microevolution. So if we go back to the super rats or super bugs or whatever super population you want to consider, before the administration of warfarin, there were very few rats that had that allele that was adapted to preventing clotting. But that was a very great advantage. So those are the individuals that survived. If you don't have to survive that rodenticide, then it's probably useless or not as important to have that particular heritable trait. But within very few years, several generations, obviously, of those rodents, a major shift into allelic frequency from very few that have the gene to prevent the allele to prevent clotting to numerous that have the gene to prevent clotting. One story that I forgot to mention referring to warfarin is the fact that warfarin was used later on to develop preventing clotting factors or medication in humans that were already suffering or suffered from a stroke or heart attack. I know I mentioned that already. Today, actually, even warfarin at different concentrations, it's explored as this anti-clotting or preventing or slowing or reducing the level of clotting in individuals that are in danger of future events such as heart attack or stroke due to clots. So, considering microevolution, take a look at this picture right here and tell me, is this population of butterflies evolving? And how did you determine that? It's obviously not evolving. 3 generations in a row, there is no change in the allelic frequency. There are very few white butterflies, which probably it's a disadvantage. Probably you're not as well camouflated. So in these 3 generations, at least, this particular population that you see right here, it's not evolving.